In today's session, we will discuss about what is the force due to a magnetic field. Now, let us consider a charged particle. Let me say I have a charged particle with some charge q. Now, let's say this charged particle moves with a velocity v. The charged particle has a velocity v and it is moving, and when it enters a magnetic field B, okay, we have a magnetic field B, and then we have a charged particle which is moving with some velocity v. When it enters the magnetic field, then the charged particle, moving charged particle, experiences some force. What we can say is, so we can conclude, due to a magnetic field, there is a force on the moving charged particle. We will see what are the properties of these force and how this force acts, what is the magnitude, what is the direction, and what this force can do. I will write here first, when a charged particle moving with velocity v, or I will write when a charged particle q moving with velocity v velocity v enters a magnetic field B, it experiences a force. Now here velocity and the magnetic field both have direction, both are vector v and then b, both are vector quantities. When a charged particle q moving with velocity v enters a magnetic field B, it experiences a force, and this force is given by Fs, force F is q into V cross B. F is q into V cross B, or it has a magnitude. The magnitude of the force is given by F is qvb sin theta. F is qvb sin theta. Sin theta. When a charged particle q moving with velocity v enters a magnetic field B, it experiences a force. The magnitude of this force is given by qvb sin theta. Now, how do we find the direction of the force? The direction of the force is given by Fleming's left hand rule. Here it is, Fleming's left hand rule. How can we state this? Now, stretch the first three fingers of your left hand, that is thumb, forefinger and the middle finger, mutually perpendicular to each other, so that the forefinger gives the direction of field. The direction of the field is given by the forefinger. The forefinger gives the direction of the field, and then the middle finger points in the direction of motion of the charge, the direction of velocity. Or sometimes if there are more moving charges, you can take it as I also. In some cases you can find it instead of V, you can find it as I, that is current. Now take your left hand, stretch the first three fingers mutually perpendicular to each other in such a way that the forefinger is in the direction of the field and the middle finger shows the direction of the velocity. Then your thumb will give you the direction of the thumbs gives the direction of the force. This is the direction of the force. Thumb. So forefinger means F. F will indicates the field, and middle finger I, that is current or velocity, and the thumb means THUM. M will be the motion of the conductor, or actually it is the force. The charge then will move in the direction of the force. So this force can change the direction of the charge. Now let me write the statement for this Fleming's left hand rule. Fleming's left hand rule states that if we stretch first two fingers and thumb and first two fingers of our left hand mutually perpendicular to each other, then if first finger points in the direction of magnetic field, then if first finger or forefinger points in the direction of magnetic field B, first finger points in the direction of magnetic field B, middle finger points in the direction of motion of charge, middle finger points in the direction of motion of charge, or its velocity. I can write motion of charge or its velocity v. Then the direction of the force on the charge, then the thumb gives the direction of the force. The thumb or then the direction of the force is given by the direction of thumb, or then the thumb gives the direction of force. Acting on the charge particle. It states that if we stretch the first two fingers and thumb of our left hand mutually perpendicular each other as shown in the figure, then if first finger points in the direction of the field and the middle finger in the direction of the velocity, middle finger points in the direction of motion of charge or its velocity v. V is actually a vector quantity. Then the thumb gives the direction of force acting on the charged particle. Now if I say, for a positive charge it will be like this, that is in the direction of the thumb, but if you take a negative charge it will be in the direction opposite to this. Now as I said, the magnitude of the charge is given by F is QVB sin theta. The magnitude of the charge is QVB sin theta. So this is where theta is the angle between B and magnetic field. You can write theta is the angle between B and V, that is the magnetic field and the velocity. Theta is the angle between B and V. Okay, so now let us we can take different cases of theta, like what happens if theta is 0, theta is 90 degree, theta is 180 degree, and then we can see what happens to the force. Now in this equation, if theta is 0, if theta is 0, the first case, if theta is 0, then what happens? Sin theta is 0, that is force is 0, F is minimum. If theta is 0, then force will become 0. That means I can say if the charged particle is moving in the direction parallel to the magnetic field or anti-parallel to the magnetic field, like theta can be 0 or theta can be 180 degree, then there is no force experiencing on the charge, force is 0. Similarly, if your charged particle is moving and in a direction perpendicular to the magnetic field, if theta is 90 degree, then your force will be maximum, F is QVB. F is QVB. So you can have different cases. In detail, I will explain all these things in the coming sessions.